Let's study circular motion, about things going around and around and around. In this video, we're going to consider a couple of different questions. And the first question we want to talk about is, what do you have to do to make an object travel in a curved path? Well, let's see what Newton's first law might say about that. Newton's first law says, an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction, which we would call a constant velocity, unless it's acted upon by an unbalanced force. A curved path is neither at rest nor motion with the same speed and in the same direction. So if it's neither of those things, Newton's first law tells us what we will need to make the object travel in a curved path. And the answer is an unbalanced force. Well, this is a video with an air puck in it, so let's watch and see what happens. Well, notice first of all that for a while the air puck was going around in a circle. Now, what was making it travel in this curved path? And the answer is there is a string connecting the air puck to this anchor here in the middle. And as the air puck is moving, the string is forcing the air puck to move in a curved path. And then all of a sudden this guy right here with this terrible tool of propane is going to eliminate the string, and when he eliminates the string, the puck just continues to move in a straight line. So as we watch this slowly, the puck is moving in a curved path, the string is making it move in a curved path, and we can see that as soon as we turn the string off by burning it away, the puck no longer moves in a curved path and it moves straight. So we see Newton's first law at work here. An unbalanced force, in this case a string, is making the puck move in a circular path. But if we turn off that force, we see Newton's first law saying that the puck now moves at a constant speed in a constant direction. Now, another way of looking at this also is to say what the puck really wants to do is move in a straight line. That's what Newton's first law says. The string prevents it from moving in a straight line by forcing it into this curved path. And if you turn the string off, then you see the puck moving in a straight path. So what you actually have illustrated here is the fact that the air puck has inertia, which means what it really wants to do all the time is go straight. And it is this string that's preventing it from doing it at all times. Now let's also look at what would be the direction of this force. So if I'm going to have a force acting on this puck, the direction of the force is actually going to be inwards towards the center of the circle. If you think about it, if a string is providing this force, strings are very bad at pushing. Strings are only good at pulling. So the direction of this force is actually inwards towards the center of the circle. So here we actually have a simulation of the same situation. We've got a green ball moving around, and we've got the vectors drawn on it. So let's see what they mean. You can see here that the blue vector is a velocity vector, and that's drawn this way. And notice that the velocity vector is basically just the direction that the ball is going. And you'll also notice the velocity vector, although it's not changing in the length of it, meaning it's not changing in its speed, the velocity vector is only changing in its direction. Now, what's making the velocity vector change is the force vector, and the force vector is right here. Ft, which means force of tension, is pulling inwards on the string. It is the string pulling inwards, I should say. So what's actually happening is that it is the string pulling inwards that changes the direction of the velocity vector. The puck at all times wants to go straight. The puck would like to follow this direction. But it is this string that keeps pulling the puck velocity vector into a curved path. So the tension in the string keeps changing the velocity vector. And then finally, you'll also notice there's a green vector, which is also inward, and that's the acceleration. That, as we're going to talk about in a moment, this puck is actually accelerating even though it moves at a steady speed. And the reason that the acceleration vector is also inward is, according to Newton's second law, whatever the direction of the force is, that's the direction of the acceleration. So let's summarize here before we move on. What we've learned so far is that a force is needed to make an object travel in a circular path. We've also learned that the direction of this force is inward towards the center of the circle. Therefore, this force is called a centripetal force. Centripetal is another word that means towards the center. Now, this word centripetal is frequently confused with another word, centrifugal. And centripetal forces are definitely not centrifugal. And we're going to talk about that and actually demonstrate in class what it exactly means to talk about something being a centrifugal force. Here's a second question that's related to the air puck going around in a circle. Is it possible for something moving at a constant speed to be accelerating? In other words, when the air puck was gliding around in that video, it was moving at a very steady speed. So is it possible that that is still could be accelerating? Now the answer to that question is yes. Something moving at a constant speed could be accelerating. In fact, things going around in circles, even at a constant speed, are accelerating. And I'm going to show you not one, but two ways that that's true. And the first way is from the definition of acceleration. Acceleration is equal to the change in velocity with time. Now, the key to realizing that something could be moving at a constant speed but still accelerating is the fact that this definition for acceleration, that word is not speed, it's velocity. So you could ask the question, well, what's velocity? Velocity is a combination of speed and direction. It's both of those things. So it turns out that you can accelerate two ways. You can accelerate if your speed is changing, and that's what you and I normally call accelerating. But it turns out that you can accelerate also if your direction is changing. Now, in our normal English language, we don't normally call direction changing as accelerating. We're used to calling speed changing being accelerating. But nature doesn't really care what we call it. In nature, a constantly changing direction is accelerating, just like a constantly changing speed. So what we're saying here is there are two ways to accelerate. Now, way number one is acceleration is change in speed with time in a constant direction. So that's like you're driving on Creek Road and you change your speed, and we would call that accelerating. Now your body inside the car, when you speed up, you feel your body move backwards in the car. So your body is a detector of acceleration. Your body is saying, yes, I'm accelerating because my body moves towards the back of the car. If I decrease my speed with time, my body moves forward. If my speed doesn't change, my body doesn't move in the car. So my body in a car is actually a very good acceleration detector. But here is another way to accelerate. And that is if my speed is constant, but my direction changes with time. So just like the air puck was always, when it went in a circle, always changing its direction. So that is just as legitimate a type of acceleration as this. And again, your body in a car could be a proof of that. And here's what I mean by that. If you take an exit ramp, so you're coming down the hill into Lewiston and you take that big long exit ramp onto Center Street, you can do that ramp at a very constant speed. but your direction will be changing with time. And think about what happens. As you turn the steering wheel to the right, your body moves to the left. So again, because your body is moving independently of the car, you are accelerating. That is just as real an acceleration as if your speed was changing. So circular motion is an example of accelerating in this way. So that's one way to show that you can move at a constant speed but be accelerating. But I told you that I was going to give you two ways that I know that something that I'm moving at a constant speed can be accelerating. So this is another way that I can prove that even though the air puck connected by that string was moving in a circle at a constant speed, it was still accelerating. And this way is by using Newton's second law. Newton's second law says acceleration equals F net over mass. So according to Newton's second law, if there is a force, there's an acceleration. Now, Newton's first law told us that an object traveling in a circle requires a force. That what an object really wants to do is move at a constant velocity, wants to move at a constant speed in a straight line. Therefore, to make it go in a circle, you will need a force. According to Newton's second law, if you have a force acting on something, a net force acting on something, then it must be accelerating. So an object moving at a constant speed must be accelerating. Now the direction of this acceleration is towards the center of the circle. So it is called a centripetal acceleration, since centripetal means towards the center. All right, now we're going to finish up with the math. So there's three things that we want to figure out. And one is, how do you figure out the speed of something that's going in a circle? How do you figure out how much an object going in a circle is accelerating? And how would you calculate the centripetal force needed to make something go in a circle? Well, let's take the first one first. How would I figure out the speed of something going in a circle? So let's first of all, here is a nice circle. So you're going around in a circle. How do I figure out how fast you're going in that circle? Well, you use the usual speed is distance over time, just like we used way back in September. Only now the distance we're traveling is in a circle. In fact, this path would be the circumference of a circle. So if I already know that the radius of this circle is r, how do I get the circumference of the circle? And the answer would be 2 pi r, which is called the circumference of the circle. All right, now the time it takes to go once around has a special name. So the time it takes to go just once around is called the period. And it is designated by a capital T. So the speed of something going in a circle is the circumference of the circle, 2 pi r, divided by the period, which is the time it takes to go around once. Next, how do I calculate the centripetal acceleration? Centripetal acceleration is v squared over r. In other words, it is the speed that you're going around in a circle squared divided by the radius of the circle. So the faster you go, the more you're accelerating. The bigger the radius of the circle is, the less you're accelerating. Because the bigger the radius of the circle is, the less your velocity vector is being changed. It's a more gradual change in your direction. If it's a very small radius, then your velocity is being changed very rapidly. Notice also the squared, which means if I go twice as fast, I will have 4 times the acceleration rate. Finally, how do I calculate the centripetal force? Centripetal force, just like from Newton's law, would equal the mass times the centripetal acceleration. Now this is the way that they write these two formulas on the Regents reference tables. But actually it turns out to be a lot more useful to actually substitute v squared over r in place of centripetal acceleration in this formula. So what it would actually look like in practice for real problem solving is m times, instead of a, we're going to write v squared over r. So the centripetal force is mass times speed squared divided by the radius. So the bigger the mass is, the more force is needed to make it go in a circle. The faster the mass is going, the more force is needed to make it go in a circle. It's squared, which means to go around the turn twice as fast means you'll need 4 times the force. And the more force is needed to make a sharper turn. If you have a more broad turn, larger r, less force is needed. Okay, try this question and show it to me when you come back to class. A 3 kilogram mass is being made to travel in a circle of radius 2.0 meters once every 5 seconds by a rope. How much force does this rope exert?